Look up at the moon tonight. It is constantly, relentlessly falling toward Earth, but it is moving sideways just fast enough to keep missing us. Realizing that the exact same mathematical law governs that massive rock in space and a piece of fruit dropping from a branch didn't just change physics, it completely rewired how we understand the universe. Isaac Newton was born in the English countryside of Woolsthorpe in 1642. By 1661, he was a student at Trinity College, Cambridge, quietly absorbing the mathematics and natural philosophy of his day. But the defining moment of his early life wasn't a brilliant lecture or a crowded laboratory. It was a pandemic. In 1665, an outbreak of the bubonic plague forced Cambridge to close its doors. Newton packed his bags and went back to his childhood home. What followed is probably the most concentrated burst of scientific invention in human history. He didn't just sit around waiting for the plague to pass. He spent those months dismantling the boundaries of human knowledge. To truly understand physics, you have to understand motion. Things speeding up and slowing down and curving through space. The math of the time simply couldn't handle continuous fluid change. So, Newton built a new mathematical engine. He called it fluxions. Today, we call it calculus. He recognized that differentiation, which extracts an instantaneous rate of change, and integration, which accumulates infinitely many small pieces, are inverse processes. Calculus became the language of changing systems. It gave science a way to express motion precisely. But here is what I find so incredible. Calculus was just one of the things he was working on in that quiet farmhouse. While he was revolutionizing mathematics, Newton was also obsessing over light. At the time, the standard belief was that white light was pure and simple. If you passed it through a glass prism and saw colors, people assumed the glass was somehow corrupting or staining the light. Newton suspected otherwise. He set up a prism in a dark room, letting a single beam of sunlight pierce through a small hole in the window shutter. The prism spread the beam into a spectrum of colors on the far wall. But Newton noticed something crucial. The spectrum was stretched out. It was far too long to fit the ordinary assumption that all rays bend or refract equally. He realized the prism wasn't creating the colors, it was sorting them. White light is actually a compound, a mixture of all the visible colors. Because different colors refract by different amounts, the glass simply separates what is already there. To prove it, he used a second prism to recombine the colored rays, and the light turned white again. With this one elegant experiment, he turned color from a vague philosophical idea into a measurable experimental science. This optical breakthrough wasn't just a neat parlor trick. It revealed a massive hardware problem. If different colors bend at different angles, then the glass lenses used in telescopes will always focus different colors at slightly different points. This creates a blurry, rainbow-colored halo around objects, a defect called chromatic aberration. Newton concluded that as long as you use a glass lens to bend light, you can't escape this blur. His solution was purely technological. Get rid of the lens. In 1668, he built the first practical reflecting telescope. Instead of a large glass lens at the front, Newton placed a concave primary mirror at the back of the tube to collect and focus the incoming light. Because mirrors reflect all visible colors equally, there is no chromatic splitting. Before the light could reach a focus, a small, flat diagonal mirror intercepted the beam and bounced it sideways to an eyepiece. This sidelong eyepiece is the signature of the Newtonian reflector. It allowed for shorter instruments that produced much sharper images. When Newton demonstrated his reflector to the Royal Society in 1672, it caused a sensation. It earned him a fellowship and proved that theoretical physics could directly drive instrument design. Even today, the world's largest research telescopes overwhelmingly rely on mirrors, not lenses. When I look at Newton's ultimate triumph, I don't just see a book, I see a new operating system for physics. In 1687, he published the Philosophiae Naturalis Principia Mathematica, or simply the Principia. Before this, people knew that objects fell to the ground, and they knew planets moved in the sky, but they thought the Earth and the heavens played by entirely different rules. Newton proved they were part of the exact same system. In the Principia, he laid out his 3 laws of motion. First, inertia. An object stays at rest or moves uniformly in a straight line unless a net external force acts upon it. This broke with everyday intuition, turning motion without ongoing pushing into the natural baseline state. Second, force and momentum. Today, we often learn this as F equals ma, force equals mass times acceleration, but Newton actually framed it around momentum, stating that force is proportional to the time rate of change of momentum. This converted the invisible causes of motion into hard, calculable equations. Third, action and reaction. When 2 objects interact, each exerts an equal and opposite force on the other. This principle underlies everything from the recoil of a cannon to the thrust of a modern rocket. But the absolute crown jewel of the Principia was the law of universal gravitation. Newton proposed that every mass attracts every other mass. The force grows with the product of the masses and weakens with the square of the distance between them. Double the distance and the gravitational pull drops to 1/4 of its strength. This inverse square law was the key. It linked the falling apple, the arc of a fired cannonball, the ocean tides, and the orbit of the moon. He didn't just explain gravity, he transformed it from a casual observation into predictive mathematical physics. Newton's later years were a stark contrast to his solitary days in Cambridge. In 1696, he moved to London to become warden and later master of the Royal Mint. He applied his relentless analytical mind to the nation's currency, tracking down counterfeiters with the same intensity he used to track planetary orbits. In 1703, he became president of the Royal Society, and the following year he finally published Optics, detailing his decades-old experiments with light. He had delayed its release for years, highly sensitive to criticism, waiting until his fiercest critics were no longer around to argue with him. Isaac Newton died in London in 1727. He left behind a legacy that is almost impossible to overstate. He didn't just discover a few isolated facts, he gave science a completely new ambition. As he wrote, his goal was to discover the forces of nature from the phenomena of motions, and then to demonstrate other phenomena from those forces. He made nature calculable. He proved that the universe operates on testable, mathematical laws that we can actually understand and use. Newton showed us that the exact same rules apply whether you are looking through a prism on your desk or staring at the distant stars. But here's my question for you. Of all his contributions, calculus, the laws of motion, universal gravitation, or the reflecting telescope, which do you think had the greatest impact on the modern world? Let me know down in the comments. If this video sparked your curiosity, make sure to hit that like button and subscribe to LynxSifts. Think of your subscription like a gravitational pull. It keeps this channel in orbit so I can bring you more deep dives into the science and technology that shape our world. Thanks for watching, and I'll see you in the next one.